There is a function that mathematicians don't want you to know about. Although its properties are strange and its shape seems to defy logic, physicists use this function every day. Indeed, without this function, physics might fall apart. But let's think of something simple. Imagine a 1 meter by 1 meter square. The area of the square is 1 square meter. Now suppose we squish this square into a rectangle with a width of 1/2 meter and a height of 2 meters. The area of this rectangle is still 1 square meter. Let's squish this rectangle even further, giving it a width of 1/4 of a meter and a height of 4 meters. It still has an area of 1 square meter. Now imagine continuing this process until the rectangle becomes very, very thin and very, very tall. Despite this drastic change to its shape, its area is still 1 square meter. But we know the area is a type of integral, so the integral of this rectangle is always 1. Now we take this process to the extreme. Give the rectangle 0 width, infinite height, and keep its area 1. This doesn't sound like any rectangle you've ever heard of, but this infinitely squished and infinitely stretched rectangle is known to physicists as
the Dirac delta function.
The Dirac delta function exhibits the strange property of being equal to 0 everywhere except at the origin, where it jumps up infinitely high while keeping its integral equal to 1. The Dirac delta function also has the strange property that if you multiply it by another function and integrate the two, you'll get the value of the other function at x equals 0. We call this behavior the sifting property. You can even move the Dirac delta function around on the x-axis, and the result is the value of the function at the location of the spike. In this video, we'll test this sifting property using our numerical integration code. But how will we ever encode the Dirac delta function into our computer? The answer lies in another limit that produces the Dirac delta function. If you take the limit of this exponential function as epsilon approaches 0, it produces the Dirac delta function. And computers can handle limits quite well. In this code, which is available at the link in the description below, we have set up our function to be integrated as the Dirac delta function times the function to be sifted. The Dirac delta function is set up as our exponential function with a very small value for epsilon. Finally, we have the function to sift. Let's start out with a simple demonstration, f equals 1. Our sifting integral picks out the appropriate value of 1, even as we change the location of the Dirac delta function's spike. Let's up the ante and try sifting f equals x squared. Sure enough, wherever we place the spike, we get the x value squared. We can repeat this process with any function, and as long as our epsilon is small enough, we'll see that the sifting property holds. I hope you've enjoyed this little excursion into mathematically forbidden territory. What you do with this knowledge is up to you, but broach this subject with your mathematics professor at your own risk.
The Dirac delta function. Let's try a couple of those. The Dirac delta function. The Dirac delta function. The Dirac delta function.